as you start to modulate the modulation symbols, how does that not destroy the orthogonality properties of the subcarriers, because they're all going to be modulated in different ways?
Yeah. As long as you have maintained the integer multiples of cycles, then using the modulation symbol on the top of that will not destroy the orthogonality.
But you're changing the phase. I mean, some of what you're doing is changing the phase, and therefore the inter-carrier phase relationships when you modulate. So I mean, clearly it works. I just don't understand.
Yeah. Okay. So when you change the phase, right, you still will have integer multiples of cycles. So you may start at different phase shift. Let's say you instead of pure sine, now you have cosine wave, for example, right? But as long as you have full cycle, then it will still maintain the relation. If you want, you can do some sort of integration of the modulated symbol, okay, including some phase. But the basic idea, let me just use this journal to give you the basic idea. Maybe you can add the phase and then verify the calculation mathematically. But I will give you the basic idea of how we can sort of work on proving the orthogonality. So let's say I have two sine waves, one at carrier frequency f1, another at 2. So we have two f1t, another sine wave. I'm taking example of pure sine wave, but you can have some other modulation symbols when you do the calculation. So the basic idea here is if let's say we give this to one UE and give this to another UE. Okay. So as far as this UE is concerned, let's say we are sending bit A on that and bit B for user 2. So for user 1, we have a reference signal, and that has the same carrier frequency, same subcarrier frequency F. Okay. For user 2, the reference signal has 2 cycles of the sine wave. So it is trying to match with this. So at user number 1, what will happen? Okay. The received signal would have both the signals. So we'll have the signal for one user and the signal for another user. Okay. Now we will take this reference signal and multiply by our own reference signal and do the integration over that modulation symbol period, which is 66 microseconds. So then you will see A sine square at your own subcarrier frequency, and then you will have multiplication of 2 sine waves, one at one frequency, another sine wave at another frequency. So when you multiply a sinusoidal signal that has 2 different frequencies where they are multiples of some base frequency, here in this case f2 is to f1. Okay. If you do that and integrate, answer will always be 0. Okay. And I will give you one simple example of how to prove it. So let's say here is f1, and then we have f2, and let me try to make it a little more beautiful. Okay. So now let's multiply these signs. So here we have positive number. This is negative. Okay. So you will get plus minus plus minus. So you have 2 positive numbers. You'll get some sort of positive number there. Positive and negative, you'll get some sort of negative number here. Then positive, negative, you will get some negative number there. and then two negative numbers. When you multiply, you'll get some positive. Okay. So when you add them up, integration is area under the curve. Right? Integration, you are summing
Right,
up.
I agree. I mean, for the basic sine wave case, it's simple enough. But don't you start modulating those sine waves to actually turn them into
Something else? Okay, so I showed you this approach. Now, your homework assignment is add the phase and see if it messes up the orthogonal. So try to do this home and see if you run into any problem. And science
okay,
positive number case. Okay. So I had asked some students to do this exercise and they came up with the answer that, oh yes, modulation does not affect orthogonality. Okay. So if you are not yet convinced, why don't you do the work, and if you run into problems, then let me know. Then I will do the work. Okay.
Yeah, I see it now. Thank you.
Yeah, but if you're not yet convinced and if you run into problems, just let me know and I will do some calculation. Okay, any other thoughts? Any other comments?
Yes, I have one question. Towards the end of the session before the break, you drew on the whiteboard when you explained number of data subcarriers.
Yes, yes.
And on the x-axis, you shown the 6 symbols. Yeah, where is exact six symbols come from?
Oh, I see. Okay, so in the book, I mean, you have the PDF file, right? That has all the slides. So on that, we are showing you 6 subcarriers. So this is from your PDF file. Okay, let me go back to that PowerPoint slide so that you can relate to what I am talking about here. So I was trying to calculate the data rate for that example. Here. So if you look at this diagram, right, I was calculating the data rate if you have this scenario where we have 6 subcarriers, 3, 4, 5, 6. So that's why I said, okay, if we allocate 6 subcarriers to some users, what kind of data rate we can get?
Well, I understand. You use 6 subcarriers as an example, right?
Yeah, because to explain what we can get if we have this specific scenario.
Right.
Okay.
So when you have 1,200 subcarriers, so you get to 100 Mbps.
Correct.
Okay, so but that is, I mean, you use 6 symbol as an example. And then you.
Oh, I see. 6. You mean?
Not on here. I'm talking on another whiteboard. You already passed them.
Yeah. How about here? This one? Are you talking about?
Yeah, no, not this.
Oh, not this.
You remember towards the end of the session, you were explaining the number of data subcarriers.
Number of data subcarriers. Oh yeah, number of data.
And there you show right there. Yeah.
Oh, okay.
6 symbols right here.
Yeah.
So the question is how does this 6 symbol come about? I mean, I don't understand where.
How do we get 6 symbols here?
Yeah.
Oh, I see. Okay, now I understand. Okay. I think I understand, but let me try to give you the answer, Okay, so in that example, I said that we have 6 subcarriers, right, for some user.
Right.
Now, that was just one hypothetical example. In practice, you cannot give 6. You have to give minimum of 12 subcarriers because there is so-called resource block defined in LTE, and that resource block contains a dozen subcarriers. So this is that set of a dozen subcarriers. That's the minimum that you would give to the user. So if I pick, let's say, the symbol time. Okay, maybe I should run the symbol time, the first symbol 0, and if I give that user just one resource block, so it will get 12 subcarriers, right?
No, I guess my question is, in the x-axis, you have a symbol 0 to symbol 6.
Oh, this symbol 0 to symbol 6.
Yeah, so how did you come about getting 7 symbols?
Okay, see, I was answering some other question. Okay. This one, okay, now okay. How, basically your question is, why 6 and why not 7, 8?
Exactly. Right.
Okay. That we can discuss. Okay, now I understand that question. Okay, good. So this is what we will do. So we have 66 microseconds. That is the modulation symbol period. Then we had mentioned earlier that there is a so-called cyclic prefix. Okay, and that will help us with the multi-path problem, and we'll cover that in the next few minutes. One value is about 4 microseconds, 4 to 5. Okay. So you will get about 71 microseconds as your total OFDM symbol time. Total. So you have 66 microsecond modulation symbol period, and then you have cyclic prefix, and together it occupies 71 microseconds. In LTE, we have a specific timing structure defined, and according to that structure, we have so-called half millisecond slots. So that is not negotiable. It is exactly half millisecond. Cannot change that because it is defined by the standard. So now the number of OFDM symbols in a slot will be the length of the slot divided by this one symbol time. Right? These many symbols we can squeeze in. So answer will be 7. So that's why we have symbol 0 to symbol 6, total of 7 symbols. So this is how I got 7 symbols in one half millisecond slot. So did you get now?
Yes, thank you.
Answer. Okay. Very good. Any other question or concerns or doubts? Any other question?
Hi, Nisit. This is regarding, like you said, that each subcarrier will transmit the symbol 0 to 6, 0 to 6, 0 to 6, right?
Each subcarrier. Oh, you mean in this? Okay, let's go back. Yeah. Time. Yeah. So each subcarrier. Correct. Inside that half millisecond slot. Yes, that is correct.
Okay, if that is the case, then in a 20 megahertz carrier, there will be so many subscribers. So how do individual subscriber being distinguished from each other?
Oh, I see. Okay, good question. Now you will get a more accurate answer, not more accurate, rather more detailed answer later. But I will just summarize the basic idea. We have subframe that is 1 millisecond long. And we already introduced so-called slot, right? Half millisecond slot. And one gentleman asked a question, how I got 7 symbols. So we also did that simple calculation. So we have now 7 OFDM symbols within that half millisecond slot. Okay. So now what will happen is, in the early part of the subframe here, there will be some control channel. I'll just write the name, but do not worry about the full name and so on. But that control channel specifies the allocation for users. So it would say, for example, that UE number 1, I am giving you subcarrier 0 to 11. UE number 2, get your data from subcarrier 12 to maybe 35, and so on. So that information is provided as part of the control channel message. Now everyone knows where their data would be. So in this case, let's say we have UE1, subcarrier 0 to 11. So UE1 says, okay, let me get my data. So this would be for UE1. Another UE, oh, my data is subcarrier 12 to 35. A little more bandwidth for that user. Okay. And I will just write the subcarrier numbers. This would be 0, 1 up to 11. This will be 12, 13 up to 35. So basically, early part of the subframe will convey the allocation to the user. Is that helpful?
Yeah, thank you.
Okay. Okay, looks like we have one question in the question box. someone is moving ahead of us. So if I have, okay, this one, this value is called short or normal cyclic prefix. There is another value supported in LTP, 16 point, I hope I have not forgotten, 16.67 microseconds. So this is long or extended cyclic prefix. There are two values supported. Okay, so if you do the calculation, then you will have 6 symbols, 0 to 5 in a slot. So those are the two basic options. If you have short cyclic prefix, you will have 7 OFDM symbols, 0 through 6. The other hand, if you have long value of cyclic prefix, then you will have 6 symbols, 0 through 5. Okay, so hopefully you got answer to that question. Any other follow-up question or any other question? Any question at all before we move forward? So I will start my 30-second timer. If we do not get any question in 30 seconds, then we get back to the presentation. You are in control. You can control the timer. You can reset it whenever you ask a question. Who wants to reset the timer? Any courageous folks out there? We are all courageous, but we have no questions. Okay, no problem. Let's get back to the presentation. We'll give you a lot of opportunities for questions. No problem. Okay. So,
The conference has been muted.
where were we? We are done here. Okay, we need to move forward, not backward. Okay. Yes. Okay. So our OFDM system face certain challenges. So in the next few slides, we'll take a look at the challenges and how to solve those challenges. One challenge, one problem is inter-carrier interface. Okay, so let's say we have this base station E node B, one user here, another user here. This guy is allocated F1, another user F2. These are simple examples. Okay. Now, let's say no one is moving. This is a mobile cellular system. Everyone is fixed. No user movement at all. Then no problem. We have this user 1 signal. Okay. User 2 signal coming at F2. Let's say we are trying to detect user 2 signal here. So we have the signal power on F2. Interference 0 from F1. We have excellent signal to interference ratio. No problem. We will be able to detect signal coming from user number 2. We are in good shape. Now let's see what happens when user 1 starts moving. So user 1 moves toward the base station. Okay. So when the user moves toward the base station, what will happen to the subcarrier frequency? It will change. Okay. So if no movement, we would have received the user 1 signal at F1, but now after the user has moved, the user is moving toward the base station. So then we will see that the actual subcarrier frequency has changed by some amount. Okay, what kind of effect is that? Why did the subcarrier frequency change? What do we call it? It starts with D, that kind of effect. Oh, so someone is asking me a question, why it is changing. I am asking you that question, why did it change? Doppler shift. Very good. Very good. So that's called Doppler effect. Okay. So whenever the users move, then because of the Doppler effect, the actual subcarrier frequency will change. So rather than getting the signal at F1, which would normally be at 15 kilohertz, now it would be maybe 16 kilohertz or whatever, some number. Okay. So it will change. Let's see the impact of that on our detection of F2. So we are the base station trying to detect user 2 signal, and this is the signal power that we have on F1. Okay, that is on F2. Let's see how much interference we get from another user. Oh, now we are seeing non-zero interference. Earlier, when no one was moving around, right, we had zero interference. But since the user has been moving toward the base station, the actual carrier frequency changed because of the Doppler effect, and now we are seeing non-zero interference. Okay, so it is becoming difficult for the E node B to detect the signal. Now we may get worried that, oh, looks like we may have a lot of problems, but no need to worry too much. The solving ICI problem is relatively easy as long as you have adequate subcarrier spacing between two subcarriers. To begin with, you are okay. In LTE, we have 15 kilohertz spacing. So if you wish, you can take my word for it that that is good enough, sufficient, adequate to be able to detect the signal even when the users are moving. Now, I will give you some approximate numbers to give you some comfort level. Okay, let's see. There is our journal here. So what I remember is the following. We have some WiMAX related performance paper. Some folks from Intel have worked on that. Okay, so basically I think 2.5 to 3 gigahertz, around that range of carrier frequency, and 120, about 120 kilometers per hour. Okay, my numbers might be slightly off, but close enough to the actual numbers that were reported in the paper. So maybe 2 to 3 gigahertz range and 120 kilometers per hour. So they found out that up to that speed and at that carrier frequency, signal to interference ratio will still be pretty high. Okay, so the signal would be 29 dB stronger than the interference. This is the ICI caused by Doppler effect. So in that case, we can easily detect the signal without any problem. So if you are interested in such details, just let me know and I will send you the paper. But that is the basic idea. So even up to 120 kilometers per hour, we are able to easily detect the signal. Okay, because the signal to interference is quite strong. And this was the number, I think, for about 10 kilohertz spacing. So if you have 10 kilohertz spacing, this is good enough. And in LT, we have even larger spacing, right? So we can expect this to be even better for LT. So since we have larger spacing in LTE, we can even support high speeds, including maybe 350 kilometers per hour, and at some carrier frequencies maybe even 500 kilometers per hour. We should be able to maintain the connection. Okay, because our subcarrier spacing is wide enough to absorb the impact of this Doppler shift. So that's for your comfort level, that we have indeed good enough spacing. So even when the users move, we are still okay. So in summary, even though the user movements will cause Doppler shift and it will result in inter-carrier interference, still we'll be okay because the spacing between two subcarriers is wide enough, it's adequate, more than sufficient. Okay, so that is the basic performance number that I have. Okay, and the number that I mentioned about 29 dB stronger signal compared to interference, that is from the Intel research paper related to WiMAX. Okay, very good. Any questions? Just type in the question box. And thank you for the questions. We welcome, we encourage, we appreciate your questions. Another challenge that we have is inter-symbol interference. So basically, this is caused by multipath. So here we are showing you an example where the receiver gets 3 copies of the same signal. This is the direct path here. And then this path gets reflected from some building, maybe another building here. So we have reflection from that building. So even though the transmitter has sent out just one signal, receiver gets 3 copies of the same signal. Those are your multipaths. So basically, the multipaths will cause inter-symbol interference. So if you are looking at your modulation symbol here, then when you are looking at your current symbol, okay, that is your direct path, then the previous copies, okay, here, copies of your previous delayed path. So those are your paths here and here. So they will start causing you interference. So this is inter-symbol interference. Now, how do we solve this problem? To solve the inter-symbol interference problem, we have so-called cyclic prefix, cyclic extension. A relatively simple, elegant way of dealing with the multipath problem. But one thing you should keep in mind is To solve the multipath problem, we cannot rely on the rake receiver. There is no rake receiver in OFDM system because we cannot even differentiate between multipaths. Here we are showing you all these different waveforms, right? In reality, all those signals get added up at the antenna itself. Our receiver cannot even separate those signals out. So the receiver gets the combined signal. So in CDMA systems, you can separate one part from another as long as they are one chip apart. But here, no such thing, okay, because they just automatically get added up at the antenna, at the receiver antenna. So how does this cyclic prefix work? Let's take a look at that aspect. Okay. So what do we have here? Yes, we have regular OFDM symbol, some sort of modulation symbol. Under normal circumstances, we would have just sent that out of the transmitter, but we need to take care of multipath. So you said, okay, let's copy tail end of the signal, paste it at the front, copy and paste. Do not do cut and paste. If you do cut and paste, you will lose the tail. Do not do that, please. Copy and paste. Control C, Control V. Copy and paste. So you are putting this signal here. So it looks as if we were extending the cycle. That's why another name for this is cyclic extension. Right? It looks like an extension of our original cycle. Now what will happen? The multipaths will try to cause interference, ISI. So here are those delayed copies. Lot of interference. But guess what? We have messed up signal whenever there is overlap. Once the overlap is over, we have nice, good-looking sine waves here. Okay, so we can easily recover the modulation symbols on those sine waves. So the intersymbol interference still exists, ISI, but as a receiver, we can simply ignore the earlier portion of that received signal. That would be easy way, right? One way of implementing the receiver. But there are some sophisticated receivers available that will do little more intensive work. But the easiest way for the receiver would be just ignore the first few samples corresponding to the cyclic prefix, and then the rest of the time period you will have nice orthogonal subcarriers available for your detection. So this is how ISI is taken care of by using cyclic prefix or cyclic reference. Basically, we are sending the information for a little longer time period so we can absorb the multipath delay spread in the initial transition period from one symbol to the next symbol. A nice, elegant way of taking care of multipath. But it is not combining of energies like a rake receiver. Right? Here we really have to fight. We have to counteract multipath. We cannot combine the energy in the ISI time period because it's all interference. One more problem that OFDM faces is so-called high peak-to-average power ratio. Now, why do we have that? So, consider this set of subcarriers, 1, 2, 3, 4. One subcarrier carries one modulation symbol. Right? Very, very simple rule during that modulation symbol period. Now, we are sending independent modulation symbols on those independent subcarriers. So it is as if we were adding some random numbers. So when you add some random numbers, what will happen? Sometimes you may get a very big number. So that's how you get high peak to average power ratio. That even though on average you may be transmitting little power. But sometimes there is a need to transmit more power. So we have high peak power compared to the average power. So that's why we call it high peak to average power ratio problem. Oh, looks like we have one question. How about the interference at the end of the symbol in the example? Oh, ISI occurs at the frame symbol boundary. Okay, so it occurs here. Then when you start with the new one, let's say you start the new one, then you will have this one, and then you will have this. So you can always focus on the useful symbol time, modulation symbol period, and that will be good enough. Okay, so when the next symbol starts, then again you are repeating the same process. Okay, and if you are worried about, let's see if this is adequate. But if you have some follow-up question, just type your question, okay? And then I just want to make sure that I answer your question. So if you did not get your answer here, just resubmit your question. Okay. But basically, every new symbol at the beginning, we will have this extra time period. Okay. That will have cyclic prefix or cyclic action. So no need to worry about the tail. Okay. The problem would occur at this transition boundary from one symbol to the next. Whenever you are changing the symbol, this is one symbol, symbol n, and this is another symbol, time period, symbol n plus 1. So at the boundary, this problem exists. Okay, so the original, let's see, we have some questions. Original previous symbol and the delayed previous symbol doesn't match the extended symbol time. Okay, and there is no overlap at the end of the symbol. Oh, I see. Okay, let's take another look at that. Okay, and for the sake of the illustration, we have been sort of showing you large values of delay spread. But see, if I have 66 microseconds, right? Short cyclic prefix is only 5 microseconds, right? Almost 5. Okay, so it's quite small. So in this case, less than 10%. So when I draw a picture, let me draw something and see if that resolves your query. Okay, this is one, and then we copy this here. Let's go up to. Okay, very good. And let's copy that portion, paste it here. Okay, these are all direct paths. Okay, direct. Now let's have some sort, just one delayed path. Let's use the uniform color. Okay, so we have. Okay, so this would be previous symbol. We will call this current symbol. Okay, and then of course we need to have delayed copy of this here also. Okay, so these are our delayed copies. So we delayed path, or let's say reflected, whatever term you want to use, you can use that. Okay, so now what is happening? So let's observe, let's say this time period. Okay, so we have one okay, this is the previous symbol, right? Previous modulation symbol. Here. And then we have this one is current modulation symbol. So we are sending different information, different modulation symbols, right? At different time periods, during different time periods. So that's where you will see inter-symbol interface. Now let's talk about what happens within the symbol time. Within symbol time, this is the key. We have coherent addition of energy. So for example, let's pick this time instance, let's say here. So we have positive, right? They go in the same direction and they will add it up coherently. Same direction, same direction, same direction, same direction, same direction. So negative, right? They add up. So there will be slight distortion here. Slight distortion here because the peaks are slightly off depending on the value of delay spread. And so with a slight distortion here. But other than that, for most part, right, you will have very nice wave. So for example, you may have something like that, maybe something like that, and then something like that. Yes. So you will have a little bit of distortion. But other than that, for most part, we have coherent addition of energy. So both go in the same direction. Here both positive, both negative, both symbol, both parts, the direct and reflected parts going in the same direction. Positive, negative. So only during some time period, as I highlighted here, we'll have some distortion. This is the distortion. Okay. But other than that, for most parts, we'll be okay. So it's good enough for the receiver to detect this kind of total combined signal. Now, okay, let's unmute the bridge, please.
The conference has been unmuted.
Okay, any other follow-up question regarding this? Do you agree, disagree, some other opinions? So within the symbol time, both the reflected and the direct parts, right, they go in the same direction. So we have coherent addition. But when we have symbol boundaries, during the transition, we have inter-symbol interface. So we are worried about that aspect. Okay. But within the symbol, it's reasonably clean. Any other question on this issue? Are we all okay with this now? Any follow-up question? Any doubt? Any confusion?
Is it too much to ask if we can go again on this whiteboard, please?
Okay, sure. Okay. So what we are saying here is the following. We have this direct path. Okay, these are the direct paths. Okay. Let me see. I hope I do not. Okay. Yeah, I'm trying to see. Okay. So we have. Yeah, let me draw another picture. Okay. Okay. So this is our direct path. Because of the cyclic prefix, we have copied some part of the signal. This becomes our total OFDM signal. Then the reflected path would be some sort of delayed version, right, of the same signal. Okay. So this is the current symbol. Now, within this time period, within our symbol, we are not worried about the delayed path because these direct and delayed copies, they go in the same direction. So this guy is increasing, so the delayed path is increasing. This direct path goes down, the reflected path going down. Direct path going down, reflected path going down. Direct path down, reflected down. Direct going up, reflected going up. So we are moving in the same direction. So it means that if it is positive, this is positive, this is positive, you add two positive numbers, right? So you have more energy. You have this negative number, this is negative, it becomes more negative, so you have more energy. So since you are moving in the right direction, in the same direction, then we have coherent addition of energy. The coherent addition of direct and reflected path within the symbol period. So that's why we do not need to worry. There is slight distortion at the top because they do not peak at the same time. So slight distortion there. They do not cross zero exactly the same time, right? There is some time offset. So slight distortion there. Slight distortion near the valley, peak or valley. So there will be slight distortion, but still for most parts you would have reasonably clean signals. So some distortion here near the valley. So those are slight distortion areas. But other than that, we have added all the energy, right? Because we have signals going in the same direction. The problem exists at the boundary because we have one modulation symbol, right? So this is reflected copy. This is the direct path. So the problem exists at the boundary because this is different information, not the same information. It's completely different modulation symbol. Here, both the modulation symbol, it is the same, right? Same information. We have the same information going on different paths because they are just delayed copies. But here, between two symbols, between the previous symbol and the current symbol, we have entirely different piece of information. That's why there is no coherent combining of energy. Does that make sense?
Yes.
Okay, very good, very good. Any other questions?
Yes, if the delay is so large, you make it hour phase.
Okay.
Would that be the case?
Yeah, then, okay. So if we have a lot of delay, then there will be a problem. But let me give you the good news. I always have the good news. Okay. The good news is the following. In a typical mobile vehicular environment, the average delay spread is about 10 microseconds. And I think that Intel paper also has that kind of information. So if you're interested, just send me. Okay, let me do this. Let me send this to all of you. So if you're interested, you can look inside the paper. Yeah, I think that is also available in the same paper. Let me send that to you. In any case, 10 microseconds. Now the idea, and this is called the delay spread. Now I will give you very, very simple definition of delay spread. Let's say I get my direct path here, and after some time I get reflected path. Okay, I'm writing fast. Hopefully you can decode my handwriting. Okay, so let's say this value is 8 microseconds. So that would be, in simple terms, your delay spread. Okay. So the difference in arrival time instance between two paths. That's your delay spread. Okay. So now this is the simple rule that you need to follow when you are doing the network planning. The value of cyclic prefix should ideally be greater than delay spread. In LTE, we have two options for cyclic prefix. We have about 5 microseconds and about 16 microseconds. So if you have delay spread, let's say 8 microseconds, which cyclic prefix will you choose? Not a trick question. Easy question.
Extended.
Extended, right? Okay, you will choose this. So that you will always be able to absorb the impact of interstable interface. So that's the goodness, that these values are good enough, okay, to take care of most situations. In case your delay spread happens to be, let's say, 20 microseconds, and of course we are stuck to this number, right, because that's the only number, that's the largest number. So then there will be some interference, interstable interference. It will become more difficult for the receiver to decode the signal at that time. But as I said, the good news is that for most parts that will not happen. Because it typically it's 10 microseconds, so we are in good shape. I'm not worried about that at all.
So the concept of the cyclic prefix is to cancel out the portion of the delayed symbol?
Exactly right. Very good summary. Any other questions or thoughts, comments? Are we all clear now?
Just curiosity, how they come up with 4.69 or 6.6?
Yeah. Okay. So basically, I think they were just trying to aim for something around 5 microseconds. Now you just want to have one small value, one long value, so that in a given environment you can choose, right? That will give you some flexibility. By the way, WiMAX has the way it stands right now about 12 microseconds. That is the number in WiMAX, mobile WiMAX. So when Clearwire is deploying mobile WiMAX, they will be using 12 microseconds. At least LTE, we have two options, right? Smaller one and the longer one, and we can pick a suitable value for the given environment. So how they came up? So basically, they would have done some sort of statistics. And say, in some environment, 5 microseconds is good enough. Okay, but instead of choosing exactly 5, they may have chosen this little bit strange number, so that we have the exact 7 symbol, okay, within your half millisecond clock. Because we do not want to mess around with half millisecond clock. So we need to choose the cyclic prefix such that we have exactly 7 symbols. 16.67, so that we have exactly 6 symbols. That's why they would have chosen a little bit strange number like that. But the idea is it's an integer number of symbols within the half millisecond slot.
If your CP is greater or much greater than delay spread, isn't that extra portion will interfere with the previous symbol?
Oh, no. In fact, you can start decoding early. No, that will not interfere.
Okay.
Okay, no interference. It will help, but not. The only drawback of using a longer value, this value, is just more overhead, right? Because you are sending some redundant information for longer time. So your effective throughput will be slightly less, right, compared to this. Because you have more overhead. But it will not interfere. It will actually help detect the signal better. For example, what you can even do, some sophisticated receivers, they can start comparing, I hope you can see, they can start comparing the initial few samples. I'm using this pink color here, and you can start comparing with the last few samples, okay, and then you can figure out that, oh yes, you indeed got the boundary of the symbol. Right? So it will actually help you. It will not cause problems. It will actually help in detection. Any other thoughts or questions?
So in the receiver side combining technology, which one you think is more efficient, MIMO or the REC?
MIMO. Actually, there is no combining, any specific combining. This is
combining means what I mean to say, the decoding. Suppose you got to decode what best eNodeB has sent to you, right? So instead of MIMO, you were sending 4 antennas talking to each other. You have one antenna with REC receiver. Which is more efficient? And if MIMO is
difficult, so you're saying if we have MIMO, let's say 4 antennas. Okay, so this guy is sending out, let's say, symbol S1, another modulation symbol S2, another modulation symbol S3, another S4. This goes over, let's say, subcarrier F1, etc. Now what is your question? Instead of this, what option do you have?
We have a REC officer. How do we use a REC receiver?
Oh, so sorry. There is no possibility of using a REC receiver. So you can never separate two symbols. There is no way you can separate 2 symbols. Okay, in CDMA, the reason that you can separate 2 signals, 2 multipaths, is you have very, very tiny resolution. So, okay, so let me give a simple example. So in CDMA, what is your background, DO1X or UMTS?
UMTS.
UMTS?
Yep.
Okay, so you have 1 divided by 3.84 a microsecond. That is your chip resolution. So let's say close to 1/4, so 0.25. Okay, so we have 0.25 microsecond resolution. So if you have one multipath coming here, another multipath, maybe only 0.3 microsecond later, right? So you can easily separate them out without any problem. But in case of OFDMA, how do you separate them? There is no way, because the signals automatically add up at the antenna. There is no way for you to separate 2 signals. Here we have the chips, right? The time resolution is very, very tiny, very refined resolution in CDMA system. So that's why you can separate them. But in OFDMA system, there is no way of separating the signals. The minimum piece of information that you transmit is OFDM symbol. That's the minimum unit of transmission, and that takes 66 microseconds, right? So the only thing you can resolve, right, in terms of the information is this level. In CDMA systems such as UMTS and 1X, you have the unit that is this chip, tiny chip. So you can separate one chip from another chip, right? Because you have this waveform, right? This kind of waveform, 1 0 0 0 0 1, etc. So you can separate one chip from another chip, but here what you can separate is only OFDM symbol, very long. So that's why there is no way you can separate. If you had tiny OFDM symbols, let's say on the order of these kind of microseconds, yeah, then you would have been able to do that, but that is simply impractical. Okay. Does that make sense?
Thank you.
Okay. Anything else before we move forward? And we want to move forward, of course. But any question, we want to make sure that all the questions are answered.
For MIMO technology, each antenna uses the same bandwidth and same data rates. Is that correct?
Okay, same.
And will there be any interference between the?
So there will be interference, yes. So there will be interference between, those signals. Yeah. So that is correct. So, but you could. Okay. So there will be one modulation symbol here. Okay. Another modulation symbol. Now, in theory, you could have, let's say, coding and modulation. If you have parallel chain, yeah, you could in theory have some multi-code word transmission, and then you can have different sort of coding, different modulations, even on different antennas. But the same subcarriers will be used.
Okay.
Okay.
So it's coding and decoding can avoid interference between the.
So the trick is to do the decoding such that we can take care of that interference. Absolutely correct.
Okay. Thank you.
Sure. Anything else at this time? Okay. Let's get back to the presentation here. Okay.
The conference has been muted.
Okay, peak to average power ratio. Okay, so on average, maybe we are using less power, but sometimes we have the need to transmit more power, and in that case, we have high peak to average power ratio. Okay, how do we solve that problem? There are several ways. One is sort of peak clipping. Basically, let's say I need this much power. Sometimes I say, okay, I will never allow more than this much. That's it. So I will chop off the peak. Now, of course, that will cause distortion, but at least you are not going into the non-linear range of the power amplifier. That's a technique that we use. In fact, in CDMA systems today, we apply that kind of technique. Okay, peak cancellation. Now here the idea is to insert some sort of anti-peak signal. So let me give you a very simple example. Let's say I have some subcarrier like that. I have given to some user then F3, number 3. So maybe 1, 2, 3, something like that. So now what is happening is if I pick some time instant, I have plus here, right? So we are adding up two signals, 2 plus. So now we have large power, large amplitude. Because plus and plus together we need to transmit more power. So the idea is to insert some dummy signal, anti-peak. So let's say this is allocated to some user, this is also allocated. And now we have F2 that is sort of idle, not given to any other user. So we can now send dummy information here, some other information. So we'll just send this kind of signal. Now this is plus, and now we have minus here. So plus minus and plus, right? So we have reduced the overall peak. So maybe instead of going all the way here, the peak is now reduced substantially. So WiMAX has this kind of technique supported. Okay. In LTE, we have this special way of dealing with that problem in the uplink that is called SC-FDMA, single carrier frequency division multiple access. Single carrier frequency division multiple access. And that's how uplink of LTE is different from WiMAX. In WiMAX, we use traditional OFDMA in both the directions, but here the downlink utilizes the regular OFDMA. However, the uplink has a special kind of variation of OFDMA. OFDMA is a twist, and this is that twist, SC-FDMA. But basically, that's the solution to this problem, which will reduce the peak to average variation. Depending on the circumstances, maybe 3 to 6 dB improvement in your peak to average variation. Okay, we have some polls coming up. Computer is slow, looks like. Okay, good. Actually, yeah, let's skip that. Okay. We already had a lot of questions, so we want to go through the material without missing anything. Okay. Okay. Now okay, what time? Yeah, we should have a break. Okay, let's have this time a little shorter break, maybe 8 minutes. How about 8 minutes rather than 10? So let's have a short break, little shorter this time, 8 minutes. Okay, and we will resume in 8 minutes. Okay, you need to rush to wherever you need to go to. 8 minutes.